current and thus current starts falling. But as you know, current through the inductor cannot change instantly. Hence, now the inductor acts as a battery supplying current, but it slowly runs out of energy. As this end is open, the electric
cannot change,
creating a high negative voltage.
Otherwise, it will
Damage
spike.
components. Thus, we add a low voltage drop Schottky diode to create a
So
path
we
for
need
electrons.
Schottky diode.
But the
When
voltage of the load still has
Switch
high
turn
voltage
off,
spikes.
Schottky diode turn
We
off.
increase the frequency of the PWM signal such that the voltage and current by the inductor remain somewhat stable.
So the
This is also the
inductor
reason why
current
the
can
switch mode
be
power
continuous.
supply uses high frequencies. To further smooth out them, we add a capacitor in parallel.
So we add
This is a
capacitor here.
capacitor. Capacitor wants to keep the potential
So
difference constant
capacitor wants
across
to keep
itself so that it can
the
change
voltage
the current.
constant.
As the switch closes, the voltage increases to 5 volts. To resist this, the capacitor flows current through itself, raising the other terminal to 5 volts. This is possible due to the electric fields which are generated in the capacitor. But it can't flow current for a long time as the plates get charged, thus the current reduces and voltage at the other end starts dropping to the ground. Also, the capacitor starts storing the energy in its plates. After some time, the
Capacitor
plates get
store
fully
energy.
charged, thus no current can flow, and the capacitor acts as an open switch. Now, if you open the switch, then there is no source to supply voltage, and thus
Open
voltage
the
starts
switch.
falling.
Then
But as you
this
know,
have
voltage
no
across
source.
the capacitor cannot change instantly.
So the capacitor
Hence,
store
the
energy,
capacitor acts
keep
as a
it
battery
constant.
supplying current, but it slowly runs out of energy, and thus the flow of current reduces, and after some time it stops, thus the voltage drops. And we have created is the buck converter.
So we call this is
But there are
converter.
some issues, as
We
the
need
load
a
changes
switch,
the voltage,
diode,
as the load also
inductor,
changes. So
capacitor,
we need to create
and
a
a load.
feedback to change the duty cycle of the PWM signal.
So
with
we
respect
change
to
the
load.
duty
Also,
cycle
how is this
of
PWM
PWM.
signal getting generated? This is the
So
complete
this
circuit.
is the
voltage of
PWM.
the output is reduced by a voltage divider, and it is fed into an op-amp, which acts as an error
So this
amplifier.
is PWM.
This component is known as an operational
Operational
amplifier, or
amplifier.
an op-amp in short. It has 2 inputs and 1 output. The other 2 terminals are for the supply voltage. It is used to
So
amplify the
this is
difference between the
OPA,
inputs.
operation
It
amplifier.
compares both the input. If the voltage at the non-inverting input or the positive terminal is greater than the inverting one, then the output is the positive supply voltage. Or if the voltage at the inverting input or the negative terminal is greater than the non-inverting one, then the output is the negative supply voltage. In this configuration, the op-amp wants to keep both of its inputs at the same voltage, and for that, it will change its output. As the feedback is to negative input, the output varies according to the
So this
voltage
is
at the negative
PWM
input.
generator.
This can be seen as a seesaw. When the input voltage falls, the output rises. And when the input rises, the output falls. This is how the differential amplifier works. This is a triangle
So this
wave
is
generator.
triangular.
The output of the error amplifier, the wave generator, is fed to another op-amp, which acts as a comparator and outputs the PWM signal, which
The
controls the
generator
MOSFET.
PWM.
Here the negative input is a constant voltage from the differential amplifier, and the positive input is the wave from the triangle wave generator. Hence, when the triangle wave is higher than the constant voltage, the output is the positive supply voltage. Here it is plus 5 volts. And when the constant voltage is higher than the triangle wave, the output is the negative supply voltage. Here it is ground or 0 volts. This is how the comparator works.
So
The
this is
constant
the
voltage
comparator.
decreases, then the width of on time decreases, and if the voltage decreases, the duty cycle of PWM also decreases. This is a P-channel MOSFET.
So this is a
An
MOSFET.
N-channel MOSFET will turn on when the gate voltage is above the source voltage, and a P-channel MOSFET will turn on when the gate voltage is below the source voltage. So when the PWM is high, the MOSFET is off, and when the PWM is low, MOSFET is on. Hence, the duty cycle of PWM and MOSFET are opposite. As one increases, other decreases. But you may think, why not use an N-channel MOSFET? Because it is on when the gate voltage is high and off when the gate is low. Because the voltage at the gate required to turn on the N MOSFET should be higher than the source voltage, and during operation, the drain and source voltage will be almost the same. Thus we need higher than VCC at the gate to turn on the MOSFET. Hence, we use a P
So
MOSFET.
we use P
Also, we
MOSFET.
add a pull-up resistor between source and gate. This is the positive supply from the battery. These voltages are created with the help of voltage regulators. As these voltages are used only for references, thus there is no current drawn from them and no power is lost. In real cases, due to non-ideal components, some power is lost as they draw a small amount of current. Now, let's look
So
at the
this
working
is a
of the
PWM
circuit.
and
We
the
will
buck
have an input
converter.
voltage of 12 volts, and we want the output of 5 volts.
So input 12 volt, output 5 volt. And this is
Now,
triangular.
if we increase the load, the current increases, but the PWM is the same as before, hence the voltage falls. This causes the voltage at the reference to fall and thus increasing the difference between this and reference at the differential amplifier. This increases the voltage at the output and then the duty cycle of PWM decreases from the comparator, thus increasing the on-time of MOSFET and increasing the voltage at the load. Also, we can change the voltage by changing the value of the potentiometer. This change in resistance will affect the feedback voltage, thus it will change the output of the error amplifier and then change the PWM signal. Now, while designing this, some care should be taken.
So some
First, the voltage of
important
the error
cases.
amplifier should always be below this reference voltage.
So
Hence,
the
we set
error
the
should
feedback
be below
voltage
its
line such
reference.
that the voltage does not exceed 2 volts. Thus, the resistor value turns out to be 100 kilo ohm and 20K trimmer. But this will reduce the voltage to a minimum of 6 volts. Hence, we use a 100 kilo ohm trimmer. For this arrangement of the op-amp and the value of the resistor, the minimum output voltage is nearly
So
4.5
minimize
volts.
4.5
For
volt.
these values, if the load is reduced by a large amount, the reference voltage may rise above 2.5 volts as the energy storage components release their energy. This isn't an issue with this analog circuit as the error amplifier
So this
will
is
output 0 volts and
analog
this will turn off
circuit.
the MOSFET. But for a digital PWM controller,
We also can
this may
present
cause some
digital
problems to
PWM.
damage them. The second is the inputs of the comparator. In this
This is a
arrangement, they
comparator.
range from 12 to 5 volts for this feedback resistor values. And if the inputs of the comparator are reversed, then the range becomes 8 to almost 0 volts. Also, the high voltage output is towards the high end of the trimmer. This is how the closed loop buck
So
converter
we
works.
have a closed
The
loop.
voltage and current from the source are converted to lower voltage and higher current at the output. Thank you for watching.
So this is a buck converter.
Last time we looked at the work.
Hi. These three devices are
So
buck
now we
converters,
compare
and
buck
they make a
converter
great
and
alternative
the
to
linear voltage
regulators.
regulator.
In this
What
video,
are the
I'll show you in
difference
practice
between
why one
linear voltage and a buck converter.
Linear voltage regulators, like this
Linear voltage regulator.
LM7805, are so cheap and so easy to use.
So it is not PWM, it is linear regulator. So
Just supply those two pins with 7 to 16 volts.
7 to 16 volt.
Add a 10 microfarad capacitor in the input,
Input is capacitor.
another one on the output,
Another is output capacitor.
and you get steady 5 volts.
So we get 5 volt.
As we all know, nothing's perfect, and so are linear voltage regulators.
So
They are quite inefficient because they waste
Inefficient
energy and produce
because
a
linear
lot of heat.
voltage
How much heat you may ask. Let's
creates
take
a
an
lot
example.
of power
If you
loss.
want to feed your voltage regulator with 9 volts and draw 500 milliamps on the output, you will have to dissipate 2 watts of
So
heat.
you have 2
The
watts
temperature of
is
your
heat.
LM7805
So
will
it is a
definitely
kind
go
of
above
loss.
100 degrees Celsius or
So
212
the
degrees
efficiency is
Fahrenheit.
too low
If you want
because
to
you
draw
put
it
the power
or increase
into
the
the
voltage, you
resistor
might need
to
to
waste the
say,
power to reduce the voltage.
or use a buck converter.
Then we should use a buck
Probably all
converter.
computer power supplies utilize buck
Computer
converters
power
to
supply use
maximize
buck
efficiency.
converter.
You can buy buck
Increase
converters with
efficiency.
different shapes, sizes, and with different specifications.
So you can see the difference.
Another name for a buck converter
This
is
is
voltage
buck
step-down
converter.
converter, which
Voltage
describes
step
this
down.
pretty well.
So this is buck converter. We use PWM.
You feed those two pads with DC voltage,
So input 12 volt, output
and you get
5
a lower
volt,
voltage here.
12 volt into 5 volt.
The output voltage is adjusted by this potentiometer.
So you can use
For
this
example,
to adjust
Set
output
it to 5
voltage.
volts, and this little guy becomes a very efficient 5 volts
Very
voltage regulator.
efficiency. The efficiency could be higher than
Let's compare in
90%.
practice the already mentioned LM7805
So this is
linear voltage regulator.
LM7M05
This
linear
really small
voltage
buck
regulator. So very small, but the power loss is very high. So you can see we want to measure the input and output.
Both are given 12 volts on the
12
input,
volt input,
and they provide 5 volts on the output.
5 volt output. The same input 12 volt,
The driver
output
boards
5
from these
volt.
old hard drives consume approximately 450
Well,
milliamps,
450
and
ampere.
serve as my dummy load. I will measure the power consumption and
So
temperature
power
of the linear
consumption.
voltage regulator.
It is a linear voltage regulator, but it wastes a lot of
Under the
power.
same load, 15 minutes after
5
powering down.
minutes.
Only 2 minutes later, the LM7805 consumes about 420 milliamps at 12 volts. But as you can see, the power consumption drops to zero and then goes back to 420 milliamps over and over again. The LM7805 shuts down if the temperature goes too high. It can operate properly up to 125 degrees Celsius or 257 degrees Fahrenheit. Then let's check the temperature.
Temperature. So output back and the linear regulator temperature.
As you can see, it's well above the safe range. So the regulator shuts down
Shut down.
and turns on after cooling down a bit.
So because temperature is too high, so the linear regulator shut down, doesn't work.
The linear voltage regulator draws 420 milliamps at 12
So
volts,
5
which gives
volt,
us
watt,
5.04
5 watt.
watts.
Then the temperature
Now let's
increase.
check if the buck converter can finish the
Power
same
pass
task.
converter.
After
same
exactly 15 minutes, the buck converter draws only 220 milliamps at 12 volts, which is only
2.6
2.64 watts. In
So
this
only
configuration,
half.
the linear voltage regulator consumes over 90% more
Consume
power,
90% power.
which is worth considering, especially when your device is battery powered.
So linear amplifier wastes a
Now
lot
let's check
of
the
energy.
temperature.
So we check the temperature.
As you can see, the buck converter
The buck
stays
converter,
at only
38
38 degrees Celsius, or 100
38
degrees Fahrenheit.
degree,
In this example, the superiority of the buck converter is very clear.
38.
Buy an
How about
LM705
this one?
for about 30 cents, while the cheapest buck converter will cost you about $2.50.
Buck converter is more
There's one more
expensive.
thing. Because buck converters use coils, they
Coil,
cause interference in your circuits. So if you're building something sensitive like a radio,
Radio.
for example,
you
you
should
should
pick
have
up
a
a
linear voltage regulator and live with all its drawbacks. On the other
Then
hand, when
it
you're
creates
designing a
EMI
device in a small
for buck
enclosure
converter.
where proper airflow cannot be provided, a linear voltage regulator with a big and hot heatsink is probably not a good
Heat
idea.
sink. So
Now
for
we know
linear
the
regulator,
advantages
you
and
need a
disadvantages
heat
of
sink.
buck converters
Cool it
and
down.
voltage regulators. If you have any questions or want to add something, feel free to write a
So you
comment
can
below,
compare
send me a message on
one
Facebook, Twitter,
plus another power, another same power.
If you find this comparison useful, you can support me by sharing this video with your friends, giving me thumbs up, or subscribing to my channel. Thanks for watching and see you next time.
So this compare linear regulator and buck converter. So we can compare the difference. One is more efficiency. So how can we calculate buck converter capacitor?
Hey Valerie,
So this is
why
buck
are you wearing a hat with a little Q on it? Why am I wearing a triangle hat with a little Q on it?
Head.
What? Ah, because it's a charge hat. So what we're actually going to be doing is making a way for you to remember how to calculate the value of a capacitor
How can you
based on
calculate
the
this
charge
capacitor?
that needs to take in and then supply to the load to ensure that you need a certain output voltage ripple. So here we have our buck converter,
This is buck
and we're
converter.
going to look at the output currents.
So this is output current.
Remember, by looking at this node, we have current coming in from the
So we
inductor,
have to
and we have current going
put
out through the
inductor
load.
here.
That's where the majority of the current, the average current flow, will be going through
So
here.
current go here and go
But a
here.
little bit of current will be going into the capacitor and then coming back out of the capacitor. And I've drawn the
So what is the
waveform over
waveform?
here. So here's our inductor current.
So
It's going to be
inductor
a triangle
current
because
up
of
down
the
down. This current.
inductor properties and the fact that we're switching between two different states. And you're going to get this waveform, and we have our average waveform here.
So this is average current.
And that's going to be
Average
the
current.
average value through the inductor is the same as the average value through the output, so I out, same as the average value. To understand this equation, we're going to start from this basic charge equation for a
This
capacitor.
Q
And we know
equals CV.
that Q equals CV, but here we want to look at changes in voltage at the output. So we're going to look at the delta of both of
This
these.
is delta.
And because the capacitor is a constant value, it doesn't get a delta, it's just a constant. So what we can do is, if we want to get a certain ripple, so this change in the VC, because it's the same as the output voltage, it's equivalent to the output ripple. So if we want to calculate the
This
C,
is
all
output
we have to
voltage
do
ripple.
is figure out the change in the charge that we expect and divide it by the change in the output voltage,
So
the
if you
maximum
choose
acceptable
a higher
voltage
C,
change.
then delta V
So all we have to
becomes
do is
small,
figure out this charge,
which
how we
means your
expect
ripple
given
becomes
into the
smaller.
capacitor and then give it back out, and then figure out what our requirement is. Okay. To do this, now we need to calculate Q. Q is the charge.
Q is the
And
charge.
if we look at this figure, because the average inductor value is the average output,
Current average is
correct? The capacitor just has to make up this difference, and the difference is shown here. So here's charge going into
so charge
the capacitor,
into
and then
capacitor.
here we have charge coming out of the capacitor. We know that at steady state, these charges need to be equal.
So this one
So all
equal
we
to
have to
this
do
one.
is calculate one of these, this triangle of charge,
This is
and
charge.
then substitute that into here, and we can solve for the capacitance
So
that
charge.
we need.
This is
So let's do
discharge.
that. So first
So
we'll
discharge.
do the change in charge of the capacitor, and it's going to be this calculation. We notice that this is a triangle, and so we can
So
do 1/2
this is
base
the charge
times height.
of the capacitor.
Basic geometry, and now we need to define these values.
This
So
is
1/2,
the area,
the base is this full value.
the height
And T
multiplied by the
And
width
if you look
and
at this, you
divided
can
by
see that
2 because it is triangular.
T is exactly the base of this triangle.
So we
So really,
calculate the
we
area.
have T over 2. And note that this does not depend on D at all, so this doesn't depend on the duty ratio. Then we multiply by the height.
Height.
And we know that this total height, the difference here is the change in the inductor value, so your
It's
inductor
only
ripple,
the change
you do need to know that value
of the
already or
inductor
calculate it,
current.
but you can do that. Then we want half of that, so
Half.
Okay. So you
Because it is triangular.
simple equations, let's simplify this. And we'll get T delta IL over 8.
So this is delta Q equal to here.
So here's the charge that
This
is
is
going
the
into the
charge.
capacitor. Now that we have this value for the charge, we can simply take that and put it back into this equation. And we will get the capacitance value must be equal to T delta IL, the ripple of the inductor, divided by 8 times the change
This
in
is delta
the
Q. So we
output.
can put delta Q here.
So using
Divided by
this
delta V.
equation, you can calculate the capacitance that's
So
required
this is the value of
based on
capacitance
the
depends on
expected voltage
the deviation of the
requirement
inductor current,
and
the deviation of the output
inductor
voltage,
current
the
ripple.
time interval, and
The
the
reason
end.
this is important is
So we can
because
calculate
the buck
how
converter
large is
is
the capacitance
different in this calculation for the capacitance value than the boost or the buck boost converter. So for the buck converter, remember that you are looking at the triangle, the charge hat of the inductor ripple waveform, and you can calculate the minimum capacitance
So if
based on
you use a
this
large
equation.
capacitance, then
What
delta
else
V all
is that
becomes
this is an
smaller.
idealized calculation
Then your
for the
voltage will
capacitance
reduce.
value. And if you
However,
want
your
to
capacitance becomes
decrease the
larger.
ripple,
You
you
need
will
a large
increase the
space.
capacitance value to maintain a steady voltage at the output.
Okay, so we can watch the next one. So this teaches us how to choose the output capacitor.
Una batería para alimentar un circuito digital, lo más simple y económico es utilizar un regulador lineal. Sin embargo, es enorme la cantidad de energía disipada en forma de calor. Una alternativa a esto es utilizar la
So this
modulación
is
por
PWM.
amplitud. Si generamos una señal PWM de amplitud de 5 volts y un ciclo de trabajo del 50%,
So duty cycle 50%,
dividido con
we can
un
reduce
de
the
2.7
power loss.
aproximadamente. Si se incluye un transistor, esta técnica puede ser útil para ajustar la luz de un LED o de un foco.
This is
Sin embargo, para un
LED.
circuito
So you
sencillo
can
de
see the
alto
duty.
voltaje podría ser desastroso.
So
Además,
we change the
el MOSFET
duty.
que utilizo es de canal N,
This is
por
a
tanto,
10 channel.
la carga debe conectarse entre el bus de voltaje y la
So
terminal de
this is
drenaje.
MOSFET.
Para
This
poder
is a
conectar
low.
la carga entre el transistor y la tierra, utilizo un MOSFET de canal P, el IRFP 9530,
So this
y el
is
driver
MOSFET.
TC4420 para la activación de la compuerta.
And
Es
this is
necesario
cycle.
agregar un filtro pasabajas para suavizar los cambios en la tensión. Sin
So
embargo,
we use
la
a low pass
resistencia del
filter.
filtro limita la cantidad de corriente que se puede extraer del circuito. En su lugar, podemos utilizar
This is
un
the
inductor
inductor.
cuya resistencia eléctrica en corriente directa es casi nula. Pero esto trae otro problema.
So you can
Cuando el
see,
transistor es apagado, el
you
campo
can change the
magnético
duty
generado por
cycle.
el
This is the
inductor colapsa,
inductor. This is the
generando picos de
capacitor.
voltaje tan altos que pueden dañar al transistor. Para evitar lo anterior es necesario
Then we need a Schottky
para
diode.
la energía concentrada en el
Schottky
inductor
diode.
cuando el transistor está apagado. Esto se logra agregando un diodo tipo Schottky a tierra.
The Schottky diode.
Así queda terminado nuestro convertidor DC-DC, ¿cierto? Bueno, en realidad no. Si se conecta una carga y se ajusta el ciclo de trabajo, podemos tener la tensión deseada en la salida. Pero si removemos la carga, la tensión se incrementa. Pasa lo opuesto cuando se ajusta la tensión y después se conecta la carga. El circuito requiere de la retroalimentación de voltaje de salida y que se ajuste el ciclo de trabajo con base en la diferencia del valor deseado y el valor medido.
So this
En
is
este
the
video les
feedback.
mostraré cómo diseñar e implementar un circuito para regular la
So this
tensión
is
del
the circuit
convertidor de CDC
for a
sin
buck
cambiar tipo
converter.
DOC y cómo medir su eficiencia.
The major efficiency.
El primer paso en el diseño de fuentes conmutadas es definir
We in
los voltajes
12 volt.
de salida,
We out
así
5
como la
volt.
corriente de carga
Load
y la
2
frecuencia de
ampere.
computación.
And the frequency
La operación
100
de corriente
kHz.
máxima permitida y el ciclo de trabajo
So
podemos
now
calcular
calculate
el
the
valor mínimo
inductor.
para la inductancia,
We want to
la cual
learn
resulta
the
en
inductor.
alrededor de 50 microfarad.
48.9 1.5 microhenry.
ese valor,
So
así
they
que
choose
usaré uno de 100
inductor.
microhenrios.
So
Del
this is
mismo modo, si
inductor.
establecemos una variación
then
máxima de
compute
0.2 volts de
capacitor.
salida, podemos calcular la capacitancia de alrededor de
So this is the
100
value of the capacitor.
pero para no fallar,
So,
perdemos
use
la
the
capacidad
capacitor.
de 1000 microfaradios. Para medir el voltaje de salida utiliza
And then
el
MOSFET.
NSP3001.
Oh, this
Se
is
trata de
80
un convertidor
converter.
de análoga digital, ADC por sus siglas en inglés, de aproximaciones sucesivas de un canal
This
único,
is 80
con 10
converter.
bits de resolución y una interfaz SPI. Además, se puede lograr una frecuencia de muestreo de hasta 200.000 muestras por segundo, más que suficiente para nuestra aplicación. Antes de comenzar a armar el circuito, es
This is
necesario
MOSFET.
ver que los MOSFETs de canal P tienen una
The
resistencia
resistor
de
0.3.
demasiado alta. Para una corriente de salida de 2 amperes, la potencia disipada es de 1.2 watts. De
So
manera
this is
similar,
loss.
si se considera la misma corriente y la máxima caída de tensión en el diodo, la potencia disipada en este es de 1.48 watts. Lo anterior sugiere que para una potencia de salida de 10 watts, la máxima eficiencia obtenida sería del 74%.
So this is output. Output.
En su lugar, diseña una tarjeta PCB con dos MOSFETs IRFZ44N de canal N, obviamente, en medio puente H, cuya resistencia drain source es muchísimo más baja. De esta manera, también es posible sustituir el diodo para la conmutación síncrona del MOSFET inferior. Para la activación de ambos transistores se requiere de un driver con la configuración Bootstrap. En este caso utilizo el IR2110 por su accesibilidad. Una vez terminado el diagrama esquemático, empiezo a rotear todas las conexiones
So
del
this is
circuito.
the circuit
En este
layout.
punto he tratado de separar físicamente las pistas de alta corriente de las de control,
So
para
this
evitar
is
que el
the
campo
layout.
electromagnético interfiere en la conversión del ADC. Decidí fabricar la tarjeta con mi CNC,
So
aunque
sí,
para
the
ser
layout.
honesto no es muy precisa y a veces corta de más un lado que de otro. De cualquier modo,
So
el
this is
resultado
the
no luce tan mal,
PC
salvo
board.
un par de pads que quedaron pegados a una pista, nada que no se pueda arreglar. La forma más sencilla de soldar los componentes es comenzar de los más pequeños a los más grandes. Es un proceso tedioso, pero me tardaría mucho más si lo hiciera en una placa perforada. Después de casi una hora la placa está terminada. Me aseguro de que no haya un cortocircuito en las terminales de alimentación y listo. Se ve bastante bien.
So you can see.
Ahora toca el turno de la descripción de hardware. El diagrama del circuito es como sigue. Se tiene principalmente un timer, un contador de SPI, un contador de carrera libre, un contador ascendente descendente y un módulo de retardo para las señales de PWM.
And the dead time.
Cuando el timer produce un pulso positivo, el driver del SPI inicia la lectura del ADC. Al mismo tiempo, el contador de carrera libre se restablece a cero y el otro contador incrementa o reduce su cuenta dependiendo de si el voltaje en la salida es mayor o menor al valor de referencia establecido. El funcionamiento del driver SPI ya lo he explicado en otro video donde se utiliza el circuito MAX
So this is the
6675
waveform.
y un termopar para medir temperatura. En este video nos concentraremos en la descripción del contador ascendente-descendente y en el módulo de retardo de señales.
This is
Se
dead
trata
time.
de un contador simple con entradas para el reset, reloj, habilitación, dirección y un bus de 10 bits como salida. Su arquitectura es conductual dado que está descrita mediante procesos. El primero que escribimos, el secuencial, representa la dinámica de un arreglo de flip-flops. Por otro lado, el proceso combinacional describe las operaciones aritméticas sujetas a las condiciones de entrada. En este punto hay que aclarar que dada la configuración Bootstrap que tenemos, es necesario que el MOSFET inferior sea activado al menos por un breve tiempo para cargar el capacitor. Por lo anterior, el valor máximo del contador está acotado al 90%. Esto es algo cercano al 920. Del mismo modo, una vez que la cuenta llega a cero, este ya no puede disminuir. Por otro lado, el generador de tiempo muerto para las señales PWM está compuesto de una serie de flip-flops para retardar el flanco positivo de la señal de entrada, como se muestra en la figura.
It's the control.
Retardando el flanco de subida en la señal original y en su complemento se obtienen señales complementarias con tiempos muertos entre sus transiciones. Para la descripción de este componente basta con describir una entidad de retardo del flanco.
Also delay.
Esta entidad tiene los puertos para el reset, reloj, señales de entrada y salida.
And the
Agregamos
reset
una
clock.
variable genérica para poder ajustar después el número de tics que queremos retardar el flanco. Ahora utilizamos este componente para aplicarlo en la señal original y su complemento en un archivo de mayor jerarquía. La arquitectura de este nuevo componente es estructural. Una breve simulación nos hace realizar el circuito funcional. Ahora escribimos el archivo de mayor jerarquía. En este componente tenemos entradas para definir el valor de referencia mediante los switches de la tarjeta BASIS 3 y el resultado de la conversión del SPI se exhibe en los LEDs. Agregamos todos los componentes uno a uno para verificar que no haya errores. A continuación creo un nuevo proyecto en Vivado para implementar el circuito. En el archivo de pines conecto las entradas del top level a los pines del dispositivo de forma individual. Generamos el bitstream y lo descargo a la tarjeta. Afortunadamente nada se ha quemado. Conecto el multímetro y al parecer el sistema funciona correctamente. Ahora establezco el voltaje en 5 volts y conecto una resistencia de 47 ohms. El voltaje no varía en esta carga para nada. Ahora conecto una resistencia de 4.7 ohms. Con este valor tendría una corriente de salida de un poco más de 1 ampere. Aparentemente el sistema compensa la caída de tensión más o menos rápido. Sin embargo, después de un tiempo la tensión empieza a disminuir irremediablemente. Decidí agregar 2 salidas más en el circuito para inspeccionar las salidas de PWM. Conecto estas señales a otro de los conectores de la tarjeta e implemento el diseño. Con la ayuda del Analog Discovery podemos visualizar las señales PWM. Con una referencia de 5 volts, el ciclo de trabajo está algo inestable. Sin embargo, cuando conecto la carga de 4 ohms, el ciclo de trabajo incrementa casi hasta el máximo y varía mucho menos. Conecto también la salida de voltaje para tratar de averiguar por qué de esto. Una primera mirada a la señal no me ayuda del todo para determinar qué está pasando. Asumo que el ciclo de trabajo está en constante cambio debido a que la tensión tiene mucho riesgo, pero la pregunta es ¿por qué? En este punto creo que es mejor utilizar el osciloscopio. Aparentemente no hay nada malo en las señales, pero tan pronto conecto la carga, las señales se vuelven completamente erróneas. Honestamente en este momento no tengo idea de qué está pasando, así que decidí soldar un diodo de flyback a tierra. Ahora las señales lucen un poco más estables cuando conecto la carga. Sin embargo, la activación de la compuerta sigue apagándose durante unos instantes. Ahora me doy cuenta de que he olvidado una regla fundamental en el diseño electrónico. Agregar capacitores de desacoplo de los circuitos integrados. No me queda más que soldar el capacitor directamente al circuito. Vuelvo a conectar las señales del osciloscopio y la fuente y parece que todo está bien, incluso cuando conecto la carga. Sin embargo, la salida de voltaje tiene mucha variación. Pensando que puede haber ruido en la señal de referencia del ADC, agrego un capacitor a los pines de aplicación, pero esto no ayuda a resolver el problema. Pese a haber hecho previamente los cálculos, cambio el capacitor de salida por uno más grande, pero no mejor. Una vez más, agrego otro capacitor en la entrada para desacoplar la fuente, pero tampoco funciona. Después de casi una hora de probar diferentes capacitores, me doy cuenta que el problema está en el ADC. Según la hoja de datos, la diferencia no lineal, DNL, incrementa con la frecuencia de muestreo. Más importante aún, el voltaje de alimentación también afecta a dicha frecuencia. Entonces decidí muestrear 10 veces más despacio, esto es a 10 kHz, manteniendo la frecuencia de conmutación a 100 kHz. Finalmente, este cambio hace desaparecer la variación de la salida. Ahora solo resta medir la eficiencia del convertidor. Para una tensión de salida de 4.9 volts se tiene una corriente de 1 ampere, esto es 4.9 watts. Por otro lado, la fuente tiene una tensión de 12 volts y 0.47 amperes, esto es 5.64 watts. Por tanto, la eficiencia es de 86.87%. Hago lo mismo con una tensión de 10 volts. En este caso, la salida es de 9.84 volts y 2.01 amperes. Esto es 19.77 watts. Del lado de la entrada tenemos una tensión de 12 volts y una corriente de 1.93 amperes, es decir, 23.16 watts. La eficiencia en este punto de operación es de 85.9%. Nada mal. En resumen, pese a los errores iniciales del diseño del PCB, el circuito funciona bien en diferentes valores de salida. En teoría, este mismo sistema podría ser utilizado para potencias mucho mayores, pero siempre con una tensión máxima de entrada de 20 volts. Espero les haya gustado el video y que hayan aprendido algo nuevo. Como siempre me despido, no sin antes recordarles el ingenio para crear, no para destruir.
Okay, so this video shows
Workshop
FPGA
DC
for
multiplexers.
the
You'll see how
buck
several
converter. So we watch 4 videos. We compare the linear regulator and the buck converter, and we show how to calculate the output capacitor, and also use FPGA to implement a buck converter. So now I will go back to the fundamental ideas of the DC to DC buck converter. So what is DC to DC buck converter? We need input voltage, DC. We need output voltage. Because output voltage, we have to remove voltage ripple. What can we do? We have to add capacitor, right? If you need a small ripple, what can you do? You increase the capacitor. But if you increase the capacitor, what is the disadvantage? You increase your cost. You increase your size. So it is a kind of trade-off. If you reduce your capacitor, then your ripple becomes higher. So you have to learn how to calculate the capacitor. And we have a switch. The switch could be MOSFET. But if the switch turn off, then we have inductor current. Then you inductor current have no place to flow. If the inductor current has no place to flow, then what happens? It creates a spike, damage the device. So what can we do? We have to put Schottky diode. If the MOSFET turn off, then Schottky diode should turn on. Then we can keep the current as a constant current. So we learned this before. Because for inductor current, you cannot make it disconnect. Otherwise, you create huge spike, right? So can we remove the Schottky diode? No. Can you remove the MOSFET? If you do not provide the MOSFET, how can you create PWM? If you do not have Schottky diode, then if the MOSFET turn off, you create a huge spike. Then you damage your device. So we need this one, we need this one. Can we remove input voltage? If you do not have input voltage, how can you create output voltage, right? So you need input voltage, you need a MOSFET, you need Schottky diode. Can we remove the inductor? If you remove the inductor, then here you have huge voltage change. If the huge voltage change, then what is your capacitor current? Then the capacitor current, because you have PWM here, you remove the inductor, you put a line. Then when you change the voltage, then this very huge, your capacitor current becomes very huge. Then you damage your capacitor. So you need an inductor here. Can you remove the capacitor? If you remove the capacitor, then your output is like this. So, but you need a very smooth output. So you need capacitor, right? So now I have a question. This is a DC to DC buck converter. Can you change anything? Can you remove the input? Can you remove the MOSFET? Can you remove the diode? Can you remove the inductor? Can you remove the capacitor? Can you remove the load? So if your advisor give you a research article, DC to DC buck converter, and you need to create a new idea, what is your new idea? Can you change anything to save your money? Remove the input voltage, remove the MOSFET, remove the diode, remove the inductor, remove the capacitor, remove the load. No. then you cannot graduate, right? And what can you do? So you finally say, I have to give up. Because this circuit is perfect, right? No one can change it. So this is a perfect DC to DC buck converter. Everybody just use it. So you have no chance to change anything. So now we try to learn the circuit. So if the system is working in steady state, what does this mean? Means now the output is 5 volt. But at the beginning, what is this voltage? 0, right? So how about from 0 to 5? We call it is transient response, right? So we do not consider transient response, we only consider steady state condition. So we have a switching frequency. If the switching frequency is 100 kilohertz, what is your time interval? It is this one, so it is 10 microseconds. So every 10 microseconds, you have to do one switch. So from this one to this one, 10 microseconds. So do you think that 10 microseconds is very long or very short? Very short. So can you use a computer to calculate it? Maybe no. So you need hardware. So we need a quick switching. And then you can see we have T. And then you have turn on. So we call this is T. How about this one? This is DT. How about this one? This is 1 minus DT. So we call D is duty cycle, right? So we have D is duty cycle. So turn on DT. Turn off 1 minus DT. DT is the MOSFET. 1 minus DT is the diode. Okay, diode interval. Then what is the output? Then you can say, if this is 12 volt, if this is 0 volt, if this is 5 microseconds, if this is 5 microseconds, what is my average output? We have duty 50-50, input 12 volt, and when the switch turn off, 0 volt. So what is the average? 6 volt, right? So you know this is 6 volt. Then we can get 6 volt output. So you change from 12 volt to 6 volt. What is this converter? Buck converter. Buck means reduce, right? Reduce. If you want to increase, how can you call it? Boost. So we have buck converter, we have boost converter. So if you have a transformer, so we should announce here, May 12. Thursday, we move to May 29, Monday. So the time is 6:30 to 9:20 during the night. Because I will attend a conference. So you have to mark it. So 25, you don't need to come here. 29, we will be here to have a makeup class. Okay? So now we understand the fundamental idea. So what is the current? The current is output voltage divided by R. So this is V all divided by R. How about this current? Anybody has any idea about average capacitor current? So do you have any idea about average capacitor current? What is the average capacitor current? Should be what? 0. If you have a small current, for example, if you have 0.1 ampere for this current, then what is your voltage? But I is constant. So what is your voltage? So then but our time is increased. If the time becomes infinity, what is your voltage across the capacitor? Infinity. So if you have a very small current, then the capacitor voltage go to infinity. Is it possible? Impossible. So our current voltage should be constant. If the voltage keep constant, how about the current should be zero? So we have a conclusion. This current should be zero. How about this current? The ripple. So we can see the relationship. So we want to learn how about the inductor current ripple. So we have inductor here, we have load here. So we have switch here, we have diode here, we have voltage here. So now I want to discuss VL. How about VL? So you can see VL is equal to LdI Ldt, right? So how about di Ldt? It is equal to VL divided by L. Then how about IL? IL is the initial value plus VL Ldt. So if I have a very small voltage, 0.1 millivolt, L is positive, time is positive, so this is T, this is positive. So after time go to infinity, what is the current? If we have a small voltage across the inductor, 0.1 volt, after infinity time, what is the current? So you can see this is constant multiplied by time. By the time is infinity, then what is this value? Infinity. So even you have a very small volt across here, after infinity time, the current becomes infinity. So is it possible we have infinity current? Impossible. So what is the conclusion? The conclusion is in steady state, the voltage across the inductor should be equal to what? 0. And the current of the capacitor should be equal to 0. So two principles, fundamental principle. Otherwise you have a big trouble. So we can check the voltage across the inductor should be 0. The current flow into the capacitor should be 0. So I think we can stop here, and we will go back after 20 minutes.